Hey geometry friends, we are still in chapter 4 and what we're looking at is section 4.6. Today we're going to discuss isosceles and equilateral triangles. Okay, I've drawn a picture of an isosceles triangle. If you remember from the last section, we talked about isosceles triangles and we confirmed that isosceles triangle is a triangle where at least two sides are congruent. So let's say that the two sides that are congruent are these that I'm going to highlight here in red. All right, so here's my isosceles triangle. I've got two sides that are congruent. When we talk about the legs of an isosceles triangle, we are speaking specifically about those parts that I just highlighted, the two parts that are congruent. The vertex of an isosceles triangle is this uppermost angle. So it's the angle created by the legs of the isosceles triangle. And finally, we've got base angles. That would be these two lower angles in the base. And though the text didn't ask us to talk about this side here that I've highlighted in gray, let me undo that. This side here that I'm going to mark with a little hatch mark, this side is referred to as the base of an isosceles triangle. Here are two useful and important theorems. The first one is that when you have an isosceles triangle, the base angles of the triangle are congruent. So if I were given, again, even though this isn't at the bottom, these two angles are the base angles. The base angles are congruent. So if these sides are congruent, they're going to imply that these angles are congruent. Then we have the converse of the isosceles triangle theorem, which starts off with, hey, I'm walking down the street. I got this triangle where two angles are congruent. Well, if two angles in a triangle are congruent, we now know that it's isosceles because we can assume that these two sides are congruent. So angle 1 and angle 2 being congruent implies that FE and DE are also congruent. So here is an opportunity for us to demonstrate those two theorems that we just talked about. So the first thing that we have to do is to name two unmarked congruent sides. So as we look at this looks like a pyramid. We know that there's two sides that are, or two unmarked congruent angles rather. So we know that there's two angles that are congruent. Here these guys are congruent. They marked it for us. But the unmarked ones, I'm going to put in green here, would be this guy and this guy. And I'll name them. So they're angles ACB. Angle ACB is congruent to angle ABC, and they're congruent by the theorem that we just discussed, the first theorem, the isosceles triangle theorem. And the isosceles triangle theorem basically says that base angles of an isosceles triangle are congruent. Next, we're going to do this one. It says name two unmarked congruent segments. And by now you should be able to say, oh, well, if these two angles are congruent, these sides are congruent, and therefore we can say that segment AD is congruent with segment AC. Here are two important corollaries. So you remember corollaries are like mini theorems that come directly from other theorems, and it's really super easy to prove. So here are these new bits of information that we have, and now it's about equilateral triangles. And these ideas can be developed directly from the information we just talked about with our isosceles triangle. I don't know why I couldn't say that, but I couldn't. All right. So in this theorem, we have a triangle is equilateral if and only if it's equiangular. So that means if you're walking down the street, because I know I see triangles all the time, if you're walking down the street and you see a triangle and all the sides are congruent, then all the angles are congruent. Or, because of the if and only if statement, it means it can go either way. If you see an angle where all the angles are congruent, then all the sides are congruent. If the sides are congruent, it implies the angles are congruent. And here, this one says that each angle of an equilateral triangle must measure 60 degrees. And I don't think any of you would argue with either of these ideas. Here in example 2, we're going to kind of exploit those two corollaries we just talked about. And what we have is we're going to find the measure of angle y. Well, if I look at this figure, I see that I have an isosceles triangle. I can put these marks here to say that these two angles must be congruent, recognizing that the measure of angle x plus the measure of angle z plus the measure of angle y must all equal 180, lets me know that if I replace this with 60, then the sum of the measure of angle z and the measure of angle y must therefore be equal to 120, right? And so if that's the case, I know I'm going long-winded with this, guys, but I'm just doing it for the sake of mathematics, all right? If this is the case, and I know that these two angles are congruent, I can clearly say that the measure of angle z is equal to the measure of angle y, which implies from this information that it's equal to 60 degrees. Therefore, the measure of angle y is 60 degrees. If that's the case, we've got three angles here that are 60 degrees, we know that we have an equilateral triangle. And since it's equilateral, it's equiangular, implies equilateralness. Since it's equilateral, we know that this side must be 8 inches as well. And so without really any work, more logical thinking, we get that YZ, the length of YZ is 8 inches. Looking at this example 3, we're going to find the value of each variable. In this case, we need to figure out what the value of 2x, what the value of x is, and what the value of y is. Well, already looking at this, I know that these two angles, these two sides are congruent, therefore these base angles, watch this please, this is the base angle of this isosceles triangle, as is this. Notice these sides, base angles are always going to be adjacent to one of the legs of the triangle. And therefore, since these two angles must be equal, this angle must also equal 2x. Well, now it looks like each of the angles of this triangle is equal to 2x, and therefore 2x has to be equal to 60. Pause and think about that if that didn't make a whole lot of sense. And furthermore, we have 4y minus 5. If each angle is 60 degrees, then it's an equiangular triangle, therefore it's equilateral, therefore all the sides are congruent, and 4y minus 5 must equal 3. These two sides are equal, and now I've got a little bit of algebra to do to solve this. This one's the easiest one. I'm going to divide both sides by 2, and I get that the value of the variable x is 30. Over here with y, a little bit more work, but not too bad. We're going to add 5 to both sides. We get that 4y must equal 8, and therefore y is equal to 2. So this is our final example for this section, and this actually turns out to be quite a long proof. But I want to talk to you, I want you to read about the proof in the text, but I want you to read up on it and kind of follow through. But what I want to do is talk through the reasoning behind the proof first so that you can do your own research. So let's talk a little bit. The first thing that we have, we have this equilateral triangle, this larger one. And what we're given is that F, B, and D are midpoints of each of these sides. So let me use a color you can see. So we've got that this side is cut into 2 equal parts, and this side is cut into 2 equal parts, as is this side. We need to prove, and this is the kind of difficult part, we need to prove that this triangle that I'm highlighting in the center is also an equilateral triangle. And notice that we just talked about sides that have nothing to do with the triangle, at least not directly. And so what the text will have you do is prove that the three triangles on the outside that I'll highlight in yellow here, this triangle, and this triangle, you're going to prove that all three of these triangles are congruent to one another by side, angle, side. Side, angle, side. Side, angle, side. How can we get the angle to be congruent? We would get the angle by noticing that triangle AEC itself is an equilateral triangle, and therefore equilateral triangles are also equiangular. Therefore, all three of these angles are congruent. Then we're going to talk about the fact that these sides are equivalent, definition of an equilateral triangle. Then we'll talk about cutting equal things in half, create more equal things or smaller equal things. That's not really a theorem, but that's the idea that you're going to see in your text. And then what you'll talk about is the fact that you've now created three triangles, triangle DEF and EAB and BCD. You've created, or at least pointed out, three triangles that are congruent, and they're congruent by side, angle, side. Once you get that, you can then say that FD and DB and FB are all congruent because of congruent parts or corresponding parts of congruent triangles are congruent. Now that you've got these three sides congruent, then you can talk about the fact that this triangle, triangle FBD, is an equilateral triangle. It is long-winded, but I want you to be able to take a look at it and understand it in your text. Or you can even, before looking at it in your text, you can take a moment to try to think about how you would write up the information we just talked about. All right? Please give that a try, and I want to hear from you. I want you to tell me how you did, if it worked out when you compared your answer to what you saw in the text.